Hello guys, welcome back to my YouTube channel, and this is day 17 of June Daily Lead Code Challenge. And our today's problem is a DP problem. So I am not directly jump on to the DP solution. First of all, I will tell you the approach, how you can actually approach this problem, and you can make a recursive solution. And I will tell you what the problem that we are finding in the recursive solution, and how we can actually convert the recursive solution to the DP solution. And that's how we will be proceeding in this video, and after that I will tell you the code both for the recursion and also for the DP. So let's start the video with the problem statement. So the question is number of increasing paths in a grid. So you are given an m cross n integer matrix grid. So this is our matrix, and where you can move from a cell to any adjacent cell in all four directions. So it is clear, like if you are at this place, you can actually move only in four directions, like up, down, right, and left. These four directions is allowed, we can move. Then return the number of strictly increasing paths in the grid. We have to return strictly increasing paths in the grid. Just a second. Okay, so what we have to do, we have to actually return the number of strictly increasing paths in the grid such that you can start from any cell and end at any cell. So what this question is saying is, like, if you have this cell, so what you have to do, you can start, like, starting point can be any cell. So you can start from here, you can start from here, you can start from here, and you can also start from here. And what you have to do, you have to, like, if you are on any cell, let's say you are starting from any cell, you just have to move, you can move in four directions, right? Left, right, and down and up. These four directions are allowed to move. So you have to move, and what you have to do, you have to make a increasing path. By increasing path, you mean like, you are here at 1, you can go to 3, but from this one you cannot go to this one or any lesser value. You can go on to only increasing values, and you have to make the paths. And after making all the paths, like if you are starting from any cell, like in this case we have four cells, so you start from every cell, like this is allowed. You can start from any cell, so you can start from any cell, and after counting the paths from every cell, you have to just add up all the paths, and you have to return how many strictly increasing paths are there in the grid. So for example, in this, how many increasing strictly increasing paths are there, let's see. So first of all, single cell is also an increasing path. So four increasing paths we have. Like if we consider a single cell a increasing path, then from this one we can actually go to 3. So this is one increasing path. And then, like, this is the length of 2. This is the length of 2, that is a increasing path. Then from this 1 3 we can move to 4. So this is a length of 3 strictly increasing path. So this is like one more that we got. Then from this cell, if we start, like this is a individual cell that I have already added, then this, from this one I can actually move to 4. So this is one path that we got. After this, if I start the DFS call from 3, if I start traversing from 3, then from 3 I cannot move to this one because this is lesser. I can move to 4. So this is one more. And from 4 I cannot move to anywhere, but the single 4 is a strictly increasing path, but I have already added like these single cells. So how many paths we got? 4, 5, 6, 7, 8. So this is how I am getting 8 strictly increasing paths. And similarly in this one, we have 1 and 2, like only two elements. So if you start from the cell itself, so these are two strictly increasing paths. Then if you start from 1, like this is the cell that we have, this is the matrix that we have this time. So 1 and 2 is already one cell, so single cell we are counting the paths, so these are 2. And from 1, if you start, you can go to actually 2. So this is one more increasing path you have. So you will be having 3 strictly increasing paths. So let's see how we can actually address this problem. Just a second. Yeah, so we have this matrix, and we know, like, what the question is asking for. We have to tell actually total number of strictly increasing path. So hear me carefully. If question anytime it says if you require total number of paths, give me all the paths, uh, like return maximum of something, return minimum of something, like majorly they will say what are the total number of paths. Okay, if question is saying you have to return total number of paths, all the paths, or explore all the possible solutions, so in that case you get the idea of recursion, because in recursion you check, in the recursion you check all the possible paths that are available. So this is, so from this you are getting the intuition of using recursion. So how you can use the recursion, let's see that. So from the problem it is clear you can start from any cell. So you can start from any cell, I have written that, like you can start from 0 0 0 1 1 0 1 1 any cell, right? And you can actually move to any direction, like these four directions are allowed, so you can actually move to any of these four directions. So what I can do, I will start from every cell and I will go in all four directions from every cell. Like if I am on this cell, I will go to every cell and I will check if this is, if this path is increasing. Like after one, if I am getting three, like the increased number, like the bigger value, then I will move here. And if here I will check, like from here also I will check all the four directions. Like for which direction I am getting the larger value, bigger value. So I'm checking from this 3 I can actually move to this 4, and from this 4 I cannot move to anywhere else. So this is one path. So like this recursion we can make. So what we will do actually, we will start the recursion from every cell, and we will find the paths. We will find the all the strictly increasing path from every cell, and we will just add up all the paths. So in the last we will get the all the possible paths from that they are strictly increasing paths. So I hope you have got the idea. Like we can start from like, just to conclude the recursive approach, we will start from every cell, and from every cell we know we can move to all these four directions. So I will go to all four directions, and like if I am moved like in this direction, so from here also I will again check. And how will check? With the recursion. Like if I came here, the same task I will do again. So that is what recursion. So this solution you can submit, but you will get the TLE. Why TLE? Let's see that. So when you will, like when you are doing the recursion actually, like if you start from F00, let's suppose, like this is what I am doing, right? I have told you, like from every cell you will start, and you will sum up all the possible paths that you are getting from every cell, and you will get the answer in the last. So let's see, if I start the recursion call from F00, what will happen? So if I start the recursion from F00, that is nothing but this cell. So I will go to this cell. This is what your F10, right? This is your F10. Then from here you are going to F11, right? So what you are seeing is this problem, this, like these are sub problems in the recursion, like F10, F11, that like in the last you will get some value, and this will add up in this. But what you are seeing is, like from this F00 I am coming to this F10, and from this F10 I am coming to F11. But what you see, I will solve this problem here, F11. From the recursion this problem will be done here, and this problem F10 will be solved here, and this will add up in the F00. But what you see, this 10 and F11, I need to solve it again. Like what I'm trying to convey is these are the sub problems. Like in this small example I am explaining, if you start from F00, you will come to this point. You will come to here, and from here you have to do the recursion from, but you are starting from this cell. So you have to solve this F10, and you have to solve F11, and after solving this you are giving this value to F00. But when you actually start from F10, actually like you are solving F10, but this is not the initial point. But when you will come here after solving this one, you have to solve this F10 again. So this is what you are solving the same problem again and again. Can I do like this? Like when I solve this F10 here, when I do this recursion for f00. So can I actually store this value that I got from this recursion? Can I store this somewhere, like a matrix? Can I store this value somewhere, like if f for f10 I have got the solution, I can I store this value here, and can I utilize it later, so that I need not to solve these sub problems again? Yes, it is possible. That is called your memoization solution. So what we will do, we are building the DP solution with this idea, like you are utilizing already solved problems to avoid solving it again. So this is your DP approach. So what approach we are using of DP here, like the memoization solution. So what we will do actually, like the same size of matrix, one DP table we will make. Okay, one DP table we will make of same size, and in that what we will do, like if we are solving the, if we are finding the paths for f00, but in the f00 you are going to f10, f11 also, and you are getting the values for them also. So what you will do, you will store the values here, like if you are got the value for these, you will store them here, right? You will store them here, and when you actually need the values for f10, you will check in the table, are this, is this value already there, like is the problem already solved, why I need to solve it again? I will just try to, I will pick the value from here, and I will tell, like from f10 what I can do, like for f10, like this is a single cell, so single cell, and from 3 I can move to 4, so like two paths are there. So this 2 will be already solved here, and from like when I get this value, like when will I get this value, like when I will be solving here or here. So from here this value will be stored here, and when I will come to this point, I will check if this is this value already there, like is this problem already solved. This will say yes, the value is 2, so I will just put the value 2 here. I will not do again this recursion call. So this is how we are utilizing already solved problems that we will store in the DP table. So I will go through both the codes, recursive solution also and DP solution also. Like the code DP solution is also like same, code is same, but just some few changes you need to do for DP table. So let's see the recursive solution first. Okay, so what our DP solution is saying, just a second. Yes, so this is our recursive solution that I am showing you. So what we will do, like they told like like sometimes the value can be bigger, so you have to do the modulo. So this modulo for that, then I am initializing this counter value to count the total paths. And since I have told you, we can start from any cell. So from every cell, I need to call the recursive call. And what I'm doing, then I am moving, like this is the boundary base case that we need to do, because like if I am here and I went out of boundary, so in that case no strictly increasing paths can be made, so I have to return 0 in that case. And also what I'm doing, like this base case is for what, like if I am on, for example, 3, and from 3 if I am moving to 1, this is not an strictly increasing path, so in that case I will return 0. This is the base case, right? This is the base case. So this is just telling like what are the actually conditions in which I cannot get the strictly increasing paths. So that is your boundary condition, and apart from that, if you are moving from bigger value to lesser value, or like equal values, so that is what we don't want. We want increasing paths, so return 0 for that also. Then we have to explore what we have to, we want to go in all four directions and check is there any increasing paths. So I have initialized with 1. Why with 1? Because a single path is a strictly increasing path in itself. So that's why I have initialized it with 1. Then I'm going to every direction, like up, down, left, right. Okay, and I'm going to every possible, every four directions. And in the last, what I'm doing, like I have, after initializing, I am adding it all four. Why I am adding it? Because you need to give all the paths, total paths. So for that I need to add up, sum up, and then return the value. But in this case what will happen is you will find TLE here. So what I can do, I can actually do the memoization. How I will do, let me tell you that. So what you need to do, I have told you, you need to make it one DB table. So DB table is what, it is one table of same size of your grid. And what you need to do, you just need to pass it in the last. And if, like here, the changes I have done is only here. If the problem is already solved, like I have initialized with -1, so when I will start the recursion from here, and when I will come here, this problem will be solved, and I will store the answer in this dp I of j. So like, if the answer is already available, this line is saying if answer is already available, I will just return the answer. I need not to do this whole recursion again, right guys? So if the problem is not already solved, like this is saying, if the problem is already solved, just return the answer. You don't need to do the recursion again. So if the problem is not already solved, you just need to go in all four directions and find the total increasing paths, and you are storing it here. Why are you storing it? So that you can utilize it later. So this is how you can actually solve this problem, and you will not get any TLE. And this approach is DP memoization solution. So if you have understood, please like the video, and you can subscribe for more such content. Thank you.